Imagine a world where machines don't just process data, they understand it at the quantum level. Where computers can analyze millions of possibilities at once, learning patterns hidden even from the most advanced supercomputers. Sounds like science fiction? Welcome to Quantum Machine Learning, or QML, the groundbreaking intersection of quantum physics and artificial intelligence, and one of the most promising revolutions of the next decade. You're watching the Learning Studio, and in today's episode from our physics playlist, we'll explore how the strange laws of quantum mechanics are about to redefine how machines think, learn, and evolve. You can explore the entire playlist by clicking the link in the video description below. This topic belongs to our section Physics Meets AI, the computational frontier, where quantum science and intelligent algorithms come together to reshape the digital world. The quantum leap, from classical to quantum thinking. For decades, AI has relied on classical computers, machines built on bits, the binary system of zeros and ones. But the quantum world doesn't follow such simple rules. In quantum computing, we use qubits, which can exist in a superposition of both 0 and 1 at the same time. That means a quantum computer doesn't explore one path, it explores many simultaneously. Now imagine combining that power with machine learning, algorithms that adapt, predict, and find hidden structures in data. This is the essence of quantum machine learning, teaching quantum computers to learn patterns from information faster and more efficiently than classical systems ever could. How QML works, learning at the quantum level. Quantum machine learning takes traditional AI algorithms, like neural networks, clustering, and optimization, and reimagines them for quantum processors. Here's how it works in principle. Quantum data encoding, information is embedded into quantum states, allowing massive parallelism. Quantum circuits as learning models, quantum gates act like neurons, transforming inputs into outputs with incredible complexity. Measurement and feedback, the system observes outcomes and updates itself, just like training in classical machine learning. In essence, QML models don't just learn from data, they learn through quantum mechanics itself. This could unlock exponential speedups for problems like molecular modeling and material discovery, optimization in logistics and finance, cryptography and secure communication, AI-based physics simulations, and perhaps most excitingly, AI that understands quantum data directly, from particle collisions to quantum sensor readings. Where physics meets computation. Quantum machine learning isn't just about faster computers, it's about a deeper connection between information and reality. At the heart of physics lies a profound truth: information is physical. Every quantum particle carries bits of information, and every physical process can be thought of as a computation. So when we merge quantum theory with machine learning, we're not just improving algorithms, we're uncovering how the universe itself processes information. Quantum computers can exploit entanglement and interference to explore solution spaces that classical systems can't even represent. This means that QML might one day help us simulate quantum chemistry, predict biological behavior, or even assist in designing new physical laws through data-driven discovery. AI helping quantum, quantum helping AI. Here's the fascinating loop. AI helps us control and correct quantum computers, stabilizing fragile qubits and optimizing error correction. And in return, quantum computers help accelerate AI learning, solving optimization and pattern recognition problems much faster. It's a symbiotic relationship, a feedback cycle where each field amplifies the other. Already, researchers are developing quantum neural networks, quantum support vector machines, and variational quantum circuits capable of learning complex quantum phenomena. Imagine an AI that not only processes quantum data, but understands quantum systems natively. That's the promise of QML. The coming decade, quantum intelligence. Over the next 10 years, quantum machine learning will evolve from theory to reality. Major tech companies like IBM, Google, and D-Wave are already developing quantum processors designed for hybrid AI workloads. Physicists and computer scientists are collaborating to create quantum classical hybrid models, systems where quantum circuits handle high-complexity tasks while classical AI manages large-scale training. As quantum hardware matures, we'll see QML drive breakthroughs in drug discovery through molecular energy simulations, climate modeling through quantum-accelerated data analysis, next-gen encryption with quantum-safe AI algorithms, cosmological data processing, modeling the universe at unprecedented scales. In essence, QML will redefine how knowledge itself is computed. Why this matters? Quantum machine learning represents a profound shift, not just in technology, but in the philosophy of computation. It's where physics becomes intelligence, and where intelligence begins to uncover new physics. By learning to think in quantum terms, AI will cross into the domain of fundamental science, capable of reasoning about uncertainty, probability, and the nature of existence itself. This is why quantum machine learning isn't just the future of AI, it's the future of understanding the universe. You've been watching The Learning Studio, and this was our episode on quantum machine learning, where physics meets AI. Make sure to like, subscribe, and check out the physics playlist linked below for more episodes from this groundbreaking series. In our next video, we'll explore quantum sensors and AI-driven measurement systems, where precision meets intelligence at the smallest scales of nature. Because the next era of science won't just be powered by data, it will be powered by quantum learning itself.